Hi, everyone, and welcome to today's webinar, SysML and its role and place in systems engineering, presented by Zane Scott. My name is Donna Long, and I will be your host during today's webinar. Over the course of nearly 40 years, Zane has built his professional skills and expertise through a multifaceted career. As the Vice President of Professional Services at Vitech, he is responsible for leading the delivery of training and consulting services, as well as the development of educational and intellectual collateral. A frequent blogger and speaker on systems engineering topics, Zane co-authored Vitech's primer for model-based systems engineering with David Long, Vitech's president. Before Zane gets started, I have just a few housekeeping items. We will be answering questions at the end of the webinar. Please send your questions in as soon as you think of them through the question tab on the webinar control panel. Zane will answer as many questions as he can today, but if we do not get to your question, we will reach out to you after the webinar. The webinar is being recorded. If you experience connection problems during the live presentation, a recording will be made available within 1 business day. The recording will be published to Vitech's webinar archive, located on our website. At the conclusion of this webinar, a survey will open on your screen. Please take a moment to give us feedback on today's presentation or on what topics you'd like to see covered in future webinars. Now I'm going to turn the presentation over to Zane. Welcome.
Great. Thanks, Donna, and welcome everybody, and thank you for spending some time with us this morning. We're going to talk today about SysML, and we're kind of all over the roadmap in terms of what is the role of SysML and what is its place in systems engineering. It ranges from people who would urge us to think that the use of SysML represents the completion of systems engineering. If you're doing SysML, then you are doing model-based systems engineering. The other end of the spectrum are the people who say SysML is not only not sufficient, but it's really not good for a number of reasons, and they make that argument. I hope that by the time we get to the end of our time together today, that you will go away with the feeling that neither end of that spectrum is quite correct, and that the real answer lies somewhere in the middle, with SysML having a very important role in model-based systems engineering and in our practice of systems engineering in the broader world. So let's get started. Systems engineering in the 21st century presents numbers of challenges that we would have never thought about 20 years ago as being applicable for systems engineering. And lots of us don't think about these today, but when we look at our world, we see that it presents us with challenges that can be met through the application of good, sound systems engineering. If I were to say one important thing today, to the exclusion of anything else, it would be that model-based systems engineering rests on good, solid systems engineering and on good, solid engineering itself. So you cannot practice systems engineering or model-based systems engineering without that solid underpinning. When we look at the challenges that face us now, we see all kinds of opportunity for systems engineering to have a role and to contribute, and for the use of models to help us in the practice of systems engineering. So we look at things like healthcare delivery. We use systems engineering in the development of pharmaceuticals and medical devices, and those are more obvious because they're closely allied with the classic engineering disciplines of chemical engineering and mechanical and electrical engineering and software engineering with the devices. But healthcare is much broader than that. The challenges it presents are much broader than that. And so healthcare delivery is an area that can benefit greatly from the application of the principles of systems engineering and the use of tools like models in approaching those problems. We have the Internet of Things, which presents all kinds of issues, excuse me, ranging from issues around how these technologies interrelate, what kind of standard interfaces would we have for them within given systems, to the ethical and moral decisions that come from integrating everything into an Internet of Things. Closely related to the Internet of Things and to the integration of a much broader system are the problems in smart cities. What is a smart city? And Incosi has a brand new group that's been stood up to spend its time looking at smart cities. What are the problems? What are the challenges? How can we help? And there is definitely a role in there for systems engineering and for model-based systems engineering. In terms of crisis response, how do we orchestrate crisis response? How do we provide, for instance, the relief that's necessary for the aftermath of a hurricane? Particularly, how do we position the resources to provide that relief when we know that there's another one coming right behind it? When we experience so many hurricanes that we name them alphabetically and go all the way through the alphabet and into the next iteration of the alphabet, into the Greek alphabet, to get our names for the hurricanes that follow on. So how do we position and allocate and deliver those resources and respond to crisis? How do we design the crisis response systems that we use day to day, our 911 systems and first responder systems? All of those things present challenges that systems engineers can make a substantial contribution to solving. And then we should recognize that most of our economy now is a service economy. Manufacturing, including defense spending, and all of the consumer manufacturing, all of the hard goods, if you would, that are produced amount to a little less than 20% of our economy. And the rest of it has to do with services. And so how do we deliver services? How do we manage the supply of the services? How do we control their delivery? How do we craft the best ways to deliver things? And systems engineers have a role there. So all of this calls on us to deliver against complexity, to use innovation, to use diversity of thought, to integrate disciplines, and to borrow a little bit from the Incosi definition of systems engineering, for us to be a truly transdisciplinary approach to the ways that we solve problems in the 21st century. So what does this have to do with SysML? Well, in order to get into that, let's talk a little bit about what it is and where it came from. SysML, according to the Object Management Group, which originated the language as an extension subset of UML, the Object Management Group says it's a general purpose graphical modeling language for specifying, analyzing, designing, and verifying complex systems that may include hardware, software, information, personnel, procedures, and facilities. So that's a pretty broad definition and a big challenge for SysML. It consists of graphical representations with a semantic foundation for modeling system requirements, behavior, structure, and parametrics. As I said, it's a subset of UML. and it consists of 9 diagrams and the graphical symbols and the underlying meaning that are used to draw those 9 diagrams. When we look, here are the 9 diagrams. So we have 9 representations, and a diagram or a view, no matter whether we're talking about SysML or talking about a particular tool, a diagram in a tool that has a database model of the system that we're designing is an answer to a query. If we have a database that has the model instantiated in it, and we'll have more to say about this, we query the database and we say, I'd like to have the following subset of the information that you have in the model in your database. And I'd like for it to be displayed using the rules that are used to construct an activity diagram or a requirements diagram or a use case diagram. So we're querying the tool and giving it the instructions so that it can return its answer in a specific format. So each one of these 9 diagrams represents a subset of the information in a tool model returned according to specific rules. Now, what does that mean? What are the implications here? Well, the first thing that we know from its heritage is that its subject domain is extended from software to systems. So it's designed to be able to design systems and not just be limited to software. But there are things in its structure and in its symbology which are software centric. So if you show this diagram, for instance, to someone who is a software engineer or someone familiar with software development or a systems engineer with specific training or experience in software development, they'll immediately resonate with this. And so they know what this is portraying. They know how to read the diagram, if you will, because they're familiar with the symbology and the particular conventions. Now, for instance, in most of these diagrams, as in the software world, time will run top to bottom. And somebody with an orientation in that world or specific training in SysML will immediately see that. So you know what the constructs are that are depicted here. So SysML appeals and is readily usable by people from a segment of the systems engineering community, the segment that's familiar with, either by training or background or experience, with the software arena. And it resonates with them and it's readable with them. And those folks are a very important segment of the community. So when I hear somebody say SysML is not good for whatever reason, and I don't want to mess with SysML, or I don't want to include SysML in what I'm doing, that's a rather short-sighted view, because SysML is a good way to communicate with an important segment of the systems engineering community. So why am I here today to suggest that we ought to have SysML and? Well, the first thing is that SysML is a communication language. It conveys information about a model, about a design, into and out of the model itself. So remember I said that a representation, a diagram, is an answer to a query. So we have somebody out there who is wanting to know a specific set of information. So they ask for that information, and they ask for it in a particular format. They're communicating with the model. Now, in most robust tools, you can pull the information out in a particular representation. You can look at the representation and you can actually say, okay, I'd like to make some changes here. I think I'd like to insert a function between these two functions. And so they can work with that representation and use that as a way of transferring that information back into the model. So SysML operates, as do lots of other representations in the systems engineering world, as a way of communicating information both into and out of the model. Understanding SysML is necessary to communicate in this way in either direction. So you need to be able to understand what you see. When you get your answer to your query back, you need to be able to understand what you see. When you get ready to put information in, you need to understand how to do that. So SysML provides model communication for the SysML literate, for those folks who are able to read and write, if you will, in that language. So why do we say SysML and? Well, software engineers and software-related systems engineers are an important segment of the systems community, but they are a subset of the systems-related community. So the people who can communicate in SysML and who natively resonate with it are a subset of the larger community. If we go back to the challenges that I was throwing out there at first, and I intentionally selected those in order to throw out some challenges that would illustrate this. We have stakeholders, so we're all familiar with acquisitions personnel. These are folks who don't necessarily have a technical background. They may have come up through the business ranks. They work in acquisitions. They write proposals. Their forte is not reading and writing a technical language. Their forte is in the business processes of acquisitions. We have business champions, the folks who are advocating that we need the solution that we're being commissioned to design, and they don't necessarily speak software language. We have process owners. So process owners are the folks who engage in the day-to-day execution of processes, and they don't necessarily have a technical background. Program or enterprise managers may or may not have technical backgrounds. My mom and dad were both teachers, and so I grew up in an environment where one of the sayings that teachers had was, if you make your best teacher the principal, what you have is the risk that you've just lost your best teacher and you've gained a principal who's not trained or inclined to be able to fulfill the functions of that job. And the same is true with program or enterprise managers. They may be engineers, but not necessarily, and they don't necessarily speak SysML. And then increasingly in all kinds of different arenas, we have to deal with regulators. So your regulators don't necessarily come from a technical background. They may come from other backgrounds, political, bureaucratic, business orientations. So we have to communicate and respond to a great number of people. Even in the engineering community, we have the non-software systems engineers, we have industrial engineers, we have the domain engineers, mechanical, electrical, civil, chemical, all of those different kinds of engineers. We have specialists in the utilities, reliability and safety and those kinds of technical folks. And we have subject matter experts. So we have scientists and social scientists and management consultants. And these folks don't necessarily speak a language that may be common even to many of us as we work on projects. And we have to remember that we as systems engineers have the responsibility to be transdisciplinary. So we've got to take ownership of the input and information exchange with all of these folks, because we're the ones that go across all of the disciplines as we put together system solutions. So now that we've said a little bit about the need for SysML and something else, and what? So what else is there? What else should go along with SysML to make for successful model-based engineering? What I'm about to give you is a list, and it's an important list, but it's not intended to be comprehensive. So there are lots of things that need to be incorporated together with SysML in order to have successful model-based systems engineering. But three things I want to talk about. One is SysML and a broader vocabulary, SysML and a model, and SysML and a metamodel. So let's talk about the broader vocabulary. When you get ready to communicate with an audience, whether you're going to communicate in a presentation like I'm doing now, or you're going to communicate on the screen, or you're going to make a way for people to look at your model, to view it on demand. In any case, the first thing that you need to do is you need to think about, what does the audience want or need to hear or see? So what's on the audience's mind? What are they thinking? What kind of questions are they coming to you with? And you need to consider that first as you consider what you're going to present to them. The reason for that goes into the neuropsychology of communication. And that is that if I have something on my mind and you want to talk to me about something else on a related track, you've got to take care of what it is that's bothering me before you can get my attention and get to what it is that you need to communicate. And that's the second thing. What do you want or need to show them? And then think about what information satisfies those. What information is going to need to be presented in order to satisfy those needs? And then finally, you ask what format best conveys that information to that audience. And see, we return right back to where we started with the audience. The communication begins and ends with your audience. And so we need to communicate in a way that they can resonate with. Now, the practical implication for this is that with a diverse audience, we need a robust vocabulary. So if we begin by saying, hey, we're going to work in 9 diagrams. These 9 diagrams are great. They'll tell you everything you ever need to know about a system. This is a complete approach, and SysML has it all. Well, the problem is that even if you could argue that all the information you'd ever want to know is there, you probably cannot go on and argue that that means that there's no reason. Because remember, our third consideration was, what format do we put that in so that the audience can understand it, can resonate with it, can come to grips with what we're trying to say? So, and I scattered some views out around the perimeter here, just for the point of illustrating that there are numbers of other views that people, particularly in other disciplines, might resonate better with and assimilate the information that we're trying to convey more easily with them. So I don't mean to say that the views that you see around here are the only other views that there could possibly be. And lots of our tools produce views beyond the 9 SysML diagrams. And they do that because they know that they have audiences that'll want or need to see those views. So there are numbers of views that could be out there. One that's not out there, although I do have an n-squared diagram, I don't have the design structure matrix, which can become very important, particularly with industrial engineers. They resonate with that. So there are views even beyond the ones that I have here. But suffice it to say that if we limit ourselves to a particular set of views, then essentially what we're doing is we're trimming our vocabulary and our ability to communicate along with it. Remember that we need a model, and a stack of views is not a model. Now, in a hyper-technical sense, a view is a model in the sense that a model is a limited representation of a reality. So a particular view, it could be argued, is a model of that subset of information. The problem is when we talk about models in model-based systems engineering, we need to talk about what it takes to make a model that we can base our systems engineering on. And that needs to go beyond any limited representation of a subset of information about the design. So what does an MBSE model have to do? And I could spend a whole day and do on a pretty frequent occasion, spend a whole day talking about what goes into a solid MBSE model. But to give you the high level view here, models have to offer a systems view in one model. So you can't cobble together models and think that you have a system model that can then become the basis for your systems engineering. Why? Because you've got the subsets of information in the different kinds of models, and that information's not in full relationship with the information that's contained in your other models. So a number of models doesn't make a view, just as a number of views don't make a model, or a number of models don't make a model for systems engineering. It needs to offer us a complete systems view. Why is that? Because the essential properties, the behavior of the system that you're modeling emerge from the relationships. And if you don't have all of the elements in full relationship to each other, then you're not going to be able to get a grip on what's going to emerge, how that will behave, how your design is going to behave. And if you can't get a handle on that, then you can't possibly make the prediction that you need to make. The fundamental job of the systems engineer is to predict whether or not a particular design will meet the requirements that drove the creation of the design. So, okay, we have a design here. Is it going to answer the mail in terms of the reason that we're coming up with a design, a system solution for this problem? So in order to do that, we need to get a system view that'll show us how to make that prediction. Anything less is not sufficient to make the prediction. Now, the third thing that I want to talk about is that we should have a system metamodel. Why do we need a metamodel? Well, of course, a metamodel is a model of the model. So we need to build our model in a framework. And as we use this language at Vitek, we talk about the metamodel as the idea behind the structure of the model. And then we instantiate our Metamodel, which incidentally is in the public domain, and you're seeing a simplified view of it right here. But our Metamodel instantiated in a database is we call a schema. So the schema gives you a rack to rack your relationships and your entities and your attributes and your parameters to make your system model into that framework. That means that the framework is going to provide for consistency and completeness. If you're working with a robust tool, then the tool's going to look and say, wait a minute, you know, there's nothing on this shelf, or the things on this shelf that should be connected to that shelf are not connected. What's going on here? Or you connected that this way here, and you connected the same kind of thing over here in a different way, and that's not consistent. So having that schema provides the basis for model discipline and rigor. And so you need to have that available to you as well. Now, given those three things that are necessary, let's talk about some of the myths that go around with respect to SysML. SysML is very important, and I would be the last guy to get up here and advocate that we need to do without it. But we also need to see it in its rightful place. So we're going to talk about three myths. The first one is that SysML is model-based systems engineering. The second one is that SysML is the industry standard, and we'll talk about that, and we'll talk about standards actually in a little greater detail as well. And then we're going to talk about the myth that says if you want to have tool interoperability, what you need to do is adopt SysML as a standard. And we'll talk about why that's a fallacy or a myth. So let's take the first one. The first one says if you've got SysML, then you're doing model-based systems engineering. You'd be surprised how many experienced systems engineers have told me this. We're doing model-based systems engineering, we're using SysML. And that's model-based systems engineering, but it's not. Why is it not? Because there's a lot more that needs to go into it. And this harkens back to our SysML and discussion. What are the critical elements of robust model-based systems engineering? Well, as I said, you need a proven metamodel. Why do I say proven? Because it's extremely difficult to just launch out and say, okay, I'm going to design a metamodel. I'll just design that from scratch. We'll come up with that from scratch. Why? Because that's a painstaking process. It would be much smarter to look and say, are there existing metamodels that have been proven in a variety of domains and disciplines? Are there proven ways to go about having a metamodel? And then we need to instantiate that model as a schema, as an organizing force in a database model. So if you don't have the single repository model organized by a schema, then you don't really have robust model-based systems engineering, and particularly you don't have a robust tool. And then finally, as we've made the point here, we need a robust vocabulary of views with which to communicate our model. And we've talked about the effect of limiting that vocabulary. It limits your audience. When you take a slice out of your vocabulary, you take a slice out of the audience. So those three are critical elements for model-based systems engineering. Just because you have SysML doesn't mean that you have those three. So we don't know if you have a proven metamodel. We don't know if you have a schema organized database model. And if you've limited it to that 9 set of views, we know that you don't have a robust vocabulary with which to communicate with your audience. The second myth has to do with the industry standard myth, and I get this all the time as well. We need to be clear, SysML is widely used within its targeted audience. So if you stick to an arena that is pretty much made up of the targeted audience for SysML, you'll find a high degree of penetration within that audience. SysML is important to them, and they use it, and they, in some instances, are able, by being confined to their slice of the world, use it exclusively. But if industry means the broader systems engineering community, like we talked about when we talked about 21st century systems engineering, if that's what we mean by industry, then SysML is one of a number of tools, but it's not the standard. So SysML appeals and is useful to a subset of the systems engineering community. If you take software diagrams and show them to a hospital administrator who wants you to design her throughput processes from the ER to the OR to the ICU and out onto the floors, if you show her software-centric diagrams to present the way that you're modeling her systems, she's going to have difficulty. There are going to be stumbling blocks. And that's not to say that some other views would not also cause her to stumble as well. But we need to keep that to a minimum, and we need to have a broad enough vocabulary. So it's certainly not the industry standard if we look at the systems and industrial engineers who are working in those process design areas, like with hospitals and healthcare delivery. The third myth is that if we adopt a SysML standard, that's the key to tool interoperability. If every tool could output SysML, then every other tool that would subscribe to that standard could input the SysML diagrams. But keep in mind that interoperability is not a communication between the tools problem. We've seen that. We've had people introduce standard ways to transfer the data from one tool to another. Interoperability instead turns on having a common or mappable data model structure from one tool to the other. So to have a good tool is like having a good high-powered ammunition. If you're gonna be a target shooter and you wanna practice and shoot accurately, having the good high-powered ammunition is great. But if you don't have a target, if you don't know where you're shooting, it's going to be really difficult to hit it. And when you don't have a map, or the data model structure in the tool that you're targeting is not mappable to your data management tool, then you don't have a target for the data to go from and to. And that's the big problem in terms of interoperability, not in having a communication language standard, but in having a standard in your Metamodel, in your schema. SysML provides a vocabulary for communication, and it's a communication language, and among those who are literate in it, it's a good communication language. But two tools are not going to be able to interoperate without being able to map their model structures to each other. That's the key. That's why I reserved the discussion of standards till now. So what about standards? why would we use standards and where would we use them? Well, most often when somebody starts talking about standards, they're usually talking to me about the desire to make the tools interoperable. So I want to be able to use this tool and that tool, and I want to have a common communication language so that they can be interoperable. Well, we just talked about why that's a problem. Because applying the standard with your communication languages as the target is not going to get you there. What will get you there through the use of standards, if you want to be serious about tool interoperability with interoperability between models, then we need to get serious about applying the standard to the metamodels, to the schema, to the database organization in the tools, rather than simply into the communication language. So, where are we now that we went on that little journey? Well, the first thing is that SysML has definite value to an important constituency. So, I would never try to say that you ought to chuck SysML out the window, because it's very valuable. It does a good job of communicating, and as long as the folks who are using it to communicate resonate with it and understand on both ends, it works great. And we need to have that tool in our bag of tricks. But it needs to be one of a number of tools and approaches. And that's because we have an increasing call to confront problems that arise outside the traditional spaces. So we're increasingly called by complexity and by what goes on in the world to work outside the traditional bend wires and metal and put together chemical spaces. We need to get even outside of the manufacturing and hard goods arena and get into the service economy, because there are problems out there, and there are problems that we can take on and we can contribute to and we can solve. And in order to do that, we have to be able to speak the languages of the owners and stakeholders. We can't go out there and say, well, I've got a really great answer here, and if you guys will just spend some time learning how to communicate with me, then you'll be able to understand my answer. So that's why I advocate that we need SysML and. We need SysML and more than this, but we need SysML and a broad vocabulary in addition. We need SysML and a single database model, and we need SysML and a proven metamodel. So I thank you for your time and attention, and now I'd be happy to answer any questions that anybody has.
Thank you, Zane. We do have a few questions thanks to our participants. I encourage you to join the discussion now and submit your questions using the webinar control panel. First question comes from Kelly. Are you saying that other representations, EFFBD, traceability, hierarchy, diagrams, etc., are clearer than SysML? Don't they too have a special notation that needs explaining?
Yeah, they do. My experience, and I came into this through the process world. So when I first encountered systems engineering, I was working for a management consulting group doing process improvement. And we began to look for a modeling tool, and so that we could model processes. And we found and started using Vitex Core at that point. That's how I got introduced to Vitex. But in all of the days of modeling business processes, I was never forced to spend more than 2 or 3 minutes helping people understand what was there. Why? Because we would model their processes and present them to them in EFFBDs. And so you might have something that they didn't understand. For instance, we would tell them that in an EFFBD and core, the triggers are green and the data items that are transferred between functions are gray. But they were able to assimilate with that and resonate with that. Time ran left to right. So it looked pretty much like the process flow charts that they would even draw for themselves. So what you have to do is you've got to pick something that minimizes the explanation. And there will be some explanation, but I've never really encountered somebody who couldn't understand a good functional flow block diagram pretty much right off the bat.
Okay, so the next question comes from Alex. If SysML is not the industry standard, then what is the industry standard? Is there one?
I think there probably is not one. And the problem with talking about industry standard is that, and I touched on this a little in the webinar, the first question you have to ask is, what do we mean by industry? So what does industry include? And once you know the answer to that question, then you can move on to saying, what does it mean to be a standard? And I would encourage you that they're depending on where you are in the industry, there are not formal standards. If you look to the traditional standards body, ASME, ANSI, and ISO, those bodies, basically what they have put out have become standards, and people look to them for standards by having products that have worked over the stretch of time. They've stood the test of time and the test of use. And so what do you mean by time? Well, if you're talking about ASME, they were formed in 1880. If you're talking about ANSI, that's 1918. If you're talking about ISO, that's 1947. So, you know, we're talking about standards bodies that have been in existence for 100 years or more. And systems engineering, for one thing, hasn't been in existence that long. Model-based systems engineering hasn't been around that long. So I don't think we've progressed to the point where we could proclaim anything as a system, as an industry standard, to the point where we would want it and throw everything else out the window for all the reasons that I presented today.
Okay. I do encourage anybody who has a question to go ahead and submit it. The last question I have at the moment is from Chris. You showed additional beyond SysML representations. Aren't there others in addition to what you showed? I'm guessing you showed additional views.
Yes, there are. And I alluded to some of that. One of the most interesting examples that I've come across is a very interesting paper that's in the SE journal. So if you're interested in this, it was done by 3 industrial systems engineers out of SUNY Oswego, and one of the guys at that time was at Texas A&M. But they went in and studied what they called the perioperative process. They studied what happens in a hospital operating room from the time the nurse asks the patient, have you had anything to eat or drink since midnight? And those of us who have had the dubious honor of going through those things knows that question well. From that kickoff all the way through until you go feet first out of the operating room, out to a floor or the ICU or wherever you're going. So they mapped the processes, and what they were trying to do was to map the communication structures and look for any inefficiencies. They used a design structure, a set of design structure matrices, which they put together into a multi-domain structure matrix. And they map the communications with tick marks on the multi-domain structure matrix, the communication between steps in the process and between people involved. And then they said something really, 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 really important. They said, this is a great way for us as industrial engineers to think about and gather the information and report it for this problem, but it's not such a hot way for us to explain this to the process owners, to the people on the OR staff who are going to need to make improvements or fly this process. So they created themselves what they called a network diagram. And that's what attracted me to their little project, because first I had to learn what a design structure matrix was. And then once I learned that and looked at it, it looked pretty much like an n-squared diagram. So I was able to take the information on their DSM and make it into an n-squared diagram and then import it into our tool. And once I had done that, I was able to get the tool to feed out an EFFPD, and lo and behold, that looked pretty much like the network diagram that they had come up with out of their heads as a way of communicating. And that really showed me that I don't want to reject design structure matrices, because for the folks that use them, they have their place. But from the systems engineering point of view, it became my responsibility to try to make that translation and to try to make their job easier. Incidentally, they were really, really interested that I could just produce that diagram without having to come up with it and draw it out like they had to do for the network diagram.
Okay. We got another question in from David. You mentioned Vitex Metamodel is available in the public domain. Where can it be accessed? And do you have metamodels for particular domains like safety analysis, for example?
And I don't have that answer right at my fingertips. Donna, do you know where our metamodel could be accessed?
Not off the top of my head. I'd have to look for it.
If we can capture,
but we'll get back to you.
Yeah, if we can capture an email on that, we'll get back to you with that, an answer to that question.
Okay. If you have, that wraps up our final Q&A for today's presentation. If you have any questions or comments for Zane, please don't hesitate to send him an email. His address is on screen. He would be happy to hear from you with any inquiries you may have. Thank you so much for coming today. Please join us on October 8th at 8 a.m. Eastern, when we will be joined by Ray Hudson, a professor in aerospace engineering from California Polytechnic State University, who is going to talk about developing the next generation of model-based systems engineers. The link to register is available on our website. Remember that at the conclusion of this webinar, a survey will open on your screen. Please take a moment to give us feedback on today's presentation or on what topics you'd like to see covered in future webinars. That's all for today. Once again, thank you for joining us and have a wonderful day.
Thank you.